Welcome students to this video module on the topic quantum mechanics. Students, quantum mechanics is introduced to explain the microscopic realities in nature. We learned that many phenomena in nature can be explained based on classical laws of mechanics, such as the law of gravitation formulated by Galileo and Newton, the laws on electromagnetism formulated by Coulomb, Ampere, Faraday, Maxwell, and the laws of thermodynamics and statistical mechanics formulated by Clausius, Kelvin, Maxwell, and Gibbs. These were the main pillars in classical physics, and using this they were able to explain many phenomena, but it suffered serious setback when applied to many microscopic experimental observations during the end of 19th century. For example, in the case of what is known as black body radiation, these laws failed to explain completely why such a radiation spectrum is occurring. Okay, so in earlier times, the scientists were able to explain most of the phenomena with the help of the above said laws, the classical mechanics, classical laws. But they failed to explain some phenomena such as black body radiation, etc. And in order to overcome this, a scientist, Max Planck, introduced the concept of quantum mechanics. So, before going into the details of Planck's quantum theory, we'll start with the starting point of quantum mechanics, or why he introduced such a new stream in physics. The phenomena that led to introduction of quantum theory is black body radiation. Let us see what is meant by a black body. A black body is an object that can emit all waves of all frequencies, radiations of all frequencies. It can absorb all radiations falling on it. So, what is a black body? A black body can absorb all frequency radiations falling on it. It can emit radiations of any wavelength when it is heated. So, a black body is a perfect absorber and a perfect emitter. Any radiation fall on a black body will be absorbed by it. And when it is heated, it can emit any radiations. In practice, it is not easy to create a perfect black body, but we can create a good approximation, a cavity which is blackened inside with a small hole on it, so that if any radiation enter into the cavity through the hole, will be absorbed by it, because absorbed by the black surface. If any radiation reflect from it, it is not easy for the radiation to escape from that, because it is a spherical cavity with a very small hole. The radiation enter into that, then it will undergo multiple reflection inside that, so that it undergo reflection inside that till it is being completely absorbed by the black body. So it's a good approximation to a perfect black body. And another thing, we know that we just explained that a perfect black body emit all radiations. You just take the case of an iron bar. You know, when an iron bar is heated progressively, it shows color variations from dull red to bright orange red, etc. These color variations, you know, color that depends on frequencies, so it emits some frequencies from that. In that way, if you consider a black body, it emits all radiations. Okay. Now, consider a black body spectrum, or how the energy is distributed among different frequencies, and at what particular frequency most of the energy is emitted. So when we analyze a black body radiation from any black body, we can see that the radiations given out by it depends only on the temperature of the black body and not on the nature of the black body. Or for a particular temperature, the energy distribution is universal. So wherever it is, if it is a perfect black body, wherever in the universe you heat that object, at a particular temperature, the spectrum, the black body distribution will be same. So we can say that the energy distribution curve, it is a universal curve. It depends on the property. It does not depend on the properties of the walls of the cavity or anything. It depends on the temperature. And at a particular temperature, the energy density has a maximum value at a particular frequency, nu m. So you can see here a black body spectrum. It is a distribution between frequency and energy density. So first observe this graph. Okay, here you can see that frequency versus intensity distribution at different temperature. The first one is at 3000 Kelvin. You can see there is a distribution curve, and the color shown in the graph as not representing the actual radiations. It is only to distinguish various graphs we use that color. Okay, so here 5000 Kelvin, you can see the distribution curve, and then 4000 Kelvin, and then 8000 Kelvin, such that. So at whatever be the at a particular temperature, the frequency distribution, the energy distribution is a constant thing. That is why we call it as a universal graph. So wherever in the universe, if it is a perfect black body, you heat it, the intensity distribution will be the same type. Okay, so now, so that we know that as the temperature increases, the intensity distribution, energy also increases, right? Now let us take any one particular temperature radiation from this. Is now this graph, energy density in 1000 Kelvin temperature. Okay, so that we know that as the frequency increases, the energy density increases, and the energy density reaches maximum for a particular value called nu m, and here after that again the energy density decreases. So at a particular temperature, the energy density is maximum for one particular frequency, nu m. Okay, so many scientists worked on this type of distribution. And many scientists try to explain this also. So let us see who will try to explain this type of a distribution graph. The scientists would try to explain this type of a distribution graph are William Wien, Lord Rayleigh, James Jeans, etc. Many other scientists also there, but these scientists' contributions are slightly more significant in that William Wayne, Lord Rayleigh and James Jean, they try to explain this distribution graph. William Wayne, based on some thermodynamic experiments and arguments, obtained an expression for the energy density in a region nu and nu plus d nu as u nu d nu equal to 8 pi h nu cube divided by c cube e to the power minus h nu divided by k t d nu. U is the energy density, that is the energy per unit volume. So the expression for energy density in a range nu and nu plus d nu for higher frequency region. So William Wayne obtained an expression for higher frequency region. This is that higher frequency region. That is u nu d nu equal to 8 pi h nu cube divided by c cube e to the power minus h nu by k d d nu. This equation well explained the higher frequency portion of the black body radiation spectrum. At the same time, Rayleigh and Jeans, they formulated an equation for the low frequency region of black body radiation spectrum, and it goes like u nu d nu equal to the energy density u nu d nu equal to 8 pi nu square k t divided by c cube d nu. Equation number 2. K is the Planck's constant, h is K is the Boltzmann's constant, and h is the Planck's constant in these equations. And Rayleigh-Jeans equation explained the lower frequency lower frequency portion of black body radiation spectrum. But the thing is that classical theories failed to coin a single formula that could explain the black body spectrum in the entire frequency region. One equation by Wayne explained the higher frequency spectrum, and the other equation by Rayleigh-Jeans explained the lower frequency region of the spectrum. But unfortunately, they couldn't coin an equation for both these or the entire frequency range. That was the failure of the classical explanation of black body radiation spectrum. But then another scientist in 1900s, Max Planck, approached this in a new way. He understood the limitations of classical physics, and he removed this black body radiation from the framework of classical physics and put that in a new framework called quantum mechanics. He explained that oscillating charges are responsible for absorption of radiation as well as emission of radiation. When a radiation is absorbed by a body, that causes an oscillator to oscillate. A body consists of a large number of harmonic oscillators. We can consider the molecule, you know that it consists of large number of molecules. It can be treated as harmonic oscillators. Oscillators has got different frequencies. So a black body contains several such harmonic oscillators. The atomic oscillators, we can consider the atoms as an oscillator. So a black body contains several such harmonic oscillators capable of vibrating at all possible frequencies. And the frequency of radiation emitted from an oscillator is same as that of the frequency of its oscillation. And whatever be the frequency of oscillation of the oscillator, that same frequency will be the that of radiation emitted from that. So if an oscillator means atomic oscillators in a body, if an oscillator oscillates at a frequency nu1, then it will emit a frequency, radiation of frequency nu1. If it is oscillating at a frequency nu2, it emits a radiation of frequency nu2. So a black body consists of a large number of harmonic oscillators which is capable of vibrating at all possible frequencies. So based on all these type of observations, he proposed a new hypothesis called the quantum hypothesis. It states that the emission or absorption of radiation means energy. It states that the emission or absorption of radiation takes place not in continuous mode, but in discrete units or quanta of energy. So Max Planck explained that emission or absorption of energy takes place not as continuous steps, but it occur as discrete units of energy, group of energy, or he called it as quanta of energy. Each quantum of energy is called a photon. So radiation, till that time it is believed that radiation is a continuous thing, but he proposed the idea that radiation is not emitted or nor absorbed as continuous, but it is discrete groups of energy. Radiation comes or absorbed or emitted in discrete groups of energy. Each discrete group of energy is called a quanta of energy or a photon of energy. Each photon possesses an energy E equal to h nu. Each photon possesses an energy E equal to h nu, where nu is the frequency. So the energy changes with the frequency of emission or absorption. H is known as the Planck's constant. Its value is 6.626 times 10 to the power negative 34 joule second. It is a universal constant. Okay, so according to Planck's quantum hypothesis, emission and absorption of radiation takes place not in continuous steps, but in discrete units or quanta of energy, and each quanta of energy is known as a photon. The energy of photon is given by E equal to h nu, where nu is the frequency of radiation and h is the Planck's constant with a value 6.624 times 10 to the power negative 34 joule second. So the introduction of Planck's hypothesis was a revolutionary break of the black body radiation from the classical theory based on Maxwell's equations, where we used a continuum of energy states. It is replaced by a discrete set of quantized states in the new quantum theory. So according to or using quantum theory, black body considers an ensemble of quantum oscillators, consist of large number of oscillators, and they absorb and emit energy in discrete amounts. Now we'll discuss how Max Planck solved the issues related to energy distribution curve of a black body using his quantum hypothesis. Let us consider there are n number of harmonic oscillators in a cavity or in a black body, and let capital E, total energy, is represented by E. So n total n number of oscillators in a black body and the total energy is E. If total energy is E and the total number is n, then the average energy of one such oscillator is given by E bar equal to E divided by n. So totally n number of oscillators and E is the total energy, then average energy of one oscillator is given by E bar equal to E divided by n. But we know that each oscillator possesses their own energy. Energy will be different. So now there are n0 particles with 0 energy, n1 particles with energy E1, and n2 particles with energy 2E, n3 particles with energy 3E, and nr particles with energy Re. So we can write n, the total number is the sum of n0 plus n1 plus n2 etc. nr, and total energy is the sum of 0 plus En1, because there are n1 number of particles with energy E. So total energy is En1 plus n2 number of particles with energy 2E. So the total energy of that particles are 2E times n2 in that way. So the total energy can be written as in this way, equation number 5. Now we know from Maxwell's distribution law, nr, or the number of particles with an energy Re, nr equal to n0 e raised to minus Re by kt. Using this, you can write each expression for n's, that is n1 equal to n0 e to the power negative e by kt, n2 is n0 e to the power negative 2 e by kt, etc. And in the same way, that we can substitute in equation number 4. Equation number 4, n equal to n0 plus, instead of n1 we can write n0 e to the power negative e by kt plus n0 e to the power negative 2 e by kt plus etc. Now n0 is a common factor, we can take that outside and we get a bracketed term, and that can be simplified into an expression 1 minus e to the power negative e by kt to the power minus 1, and that will yield n equal to n0 divided by 1 minus e to the power minus e by kt. Okay, so this simplification you learn, we applied binomial expansion and neglecting the higher powers of that, because those terms are very, very small. So we can neglect the higher powers and simplified the equation. This is an approximately equal to this value. So we applied binomial expansion there, and then we applied eliminated the higher powers. Hence we obtained this equation for n equal to n0 divided by 1 minus e to the power negative e by kt. That is equation number 6. In the same way, equation number 5, we can substitute for equation number 5 e equal to 0 plus e times, instead of n1 we substitute n0 e to the power negative e by kt. n2 we can replace by n0 e to the power negative 2 e by kt. This is actually just a minute. This is 2e by kt, okay, etc. And here we can take n0 e exponential minus e by kt outside, then the remaining terms are as shown in the bracket, and simplifying this expression we get n0 e to the power negative e by kt divided by 1 minus exponential minus e by kt whole square. Now substituting these values of E and N, equation number 3 for the average energy E bar equal to E divided by N, we obtain N0 E exponential negative epsilon by kt divided by 1 minus exponential minus E by kt whole square divided by N0 by 1 minus exponential minus e by kt. Simplifying that, we get the expression E bar equal to E by exponential E by kt minus 1. But we know that the energy E is equal to h nu. Substituting that, we get the average energy of one oscillator is one harmonic oscillator in a black body is E bar equal to h nu divided by e to the power h nu divided by kt minus 1. But we know that the number of oscillators per unit volume in a frequency range nu and nu plus d nu, the distribution law. I'm not explaining the distribution law here. We already learned such that the number of oscillators, number of particles per unit volume in a frequency range nu and nu plus d nu, and this is the expression for the equation number 9, n nu d nu, that is the number of oscillators in a unit volume having frequency in a range nu and nu plus d nu, that is equal to 8 pi nu square d nu divided by c cube. When you multiply with number of oscillator with the average energy of one oscillator, we obtain the energy density in a frequency range nu and nu plus d nu, that is u nu d nu. U nu is the energy density, u nu d nu is the energy density in a frequency range nu and nu plus d nu, that is given by this term, that is the number density times the average energy E bar. So simplifying this, 8 pi h nu cube divided by c cube times d nu divided by e to the power h nu divided by kt minus 1. This is actually known as Planck's distribution law. This explains both the lower frequency side and higher frequency side of the black body radiation spectrum. So Planck's distribution law states, or according to this Planck's distribution law, the total or the energy density of oscillators in a frequency range nu and nu plus d nu is given by 8 pi h nu cube divided by c cube d nu divided by e to the power h nu by kt minus 1. This is Planck's distribution law. Now, finding the total energy U, the total energy density U of the black body at a temperature T. We have to integrate the energy density in a small frequency range. So integrating that, I'm not showing the integration steps anyway, that is not the primary part for us here. So after showing this integration, U is equal to 8 pi to the power 5 k to the power 4 t to the power 4 divided by 15 h cube c cube. You can see that all these terms except temperature are constants. So we can write this as U proportional to fourth power of temperature. This resembles the Stefan-Boltzmann law of radiation, which says that the power radiated per unit area by a black body is proportional to the fourth power of the absolute temperature. So using Planck's distribution law, we arrived at the total energy density proportional to the fourth power of temperature, which is similar to that of Stefan-Boltzmann distribution law. Now let us check the validity of classical theories that we discussed using Planck's distribution law that we obtained using Planck's hypothesis. For low frequency limit, we can write h nu divided by kt very much less than 1, and therefore we can expand e to the power h nu divided by kt as a power series expansion, and we obtain e to the power h nu by kt as 1 plus h nu by kt. The expansion steps we are omitting here. We are taking the final result, e to the power h nu by kt. For the power is very much less than 1. We can expand and approximate the values as 1 plus h nu divided by kt. Then using this Planck's distribution law, the equation 10 that we obtained becomes u nu d nu equal to 8 pi nu square k t divided by c cube times d nu. by substituting the e to the power h nu by kt as 1 plus h nu by kt. The 1 cancels and only h nu by kt will come the denominator. Then we can take the kt to the numerator and one of the h cancels, and that is why the equation 10 reduces to u nu d nu equal to 8 pi nu square kt divided by c cube d nu. We can see that this is exactly same as that of Rayleigh-Jeans formula. They formulated that for low frequency side of black body radiation. So hence Planck's hypothesis explains the low frequency side. Now let us see the higher frequency side. For higher frequency limit, we can write the exponential e to the power h nu by kt as very much greater than 1. As the exponential power is higher, that answer also be very much greater than 1. Substituting this in equation number 10, that is the Planck's distribution law. It become, you know, the value e to the power h nu by kt is in the denominator, as that factor is very much greater than 1. We can neglect the 1 in comparison with the exponential term, because that answer e to the power h nu by kt is much greater than 1. So we can neglect the e to the power h nu by kt minus 1, this 1. We can neglect this 1 factor there, and what is remaining in that expression. So you can see that e to the power h nu by kt we can take to the numerator. That is why it became negative e to the power negative h nu by kt. Okay, so the final expression for higher frequency limit simplified to u nu d nu. What is that? Energy density of particles having frequency in a range nu and nu plus d nu is u nu d nu equal to 8 pi h nu cube divided by c cube times exponential negative h nu by kt d nu. This is exactly the Wien's law that we learned for higher frequency limit. Hence, using equation 10, that's a Planck's distribution law, we satisfactorily explained the lower frequency side of black body spectrum and the higher frequency side of black body radiation spectrum. So Planck's hypothesis successfully explained the black body radiation spectrum, and this was the beginning of quantum mechanics. Thank you, students.